Yep, thank you for the introduction. So my background is mostly in geometry, which is closer to mathematical physics. So actually, I just learned about this topic of deep learning like around 2 years ago. And when I first learned about deep learning, so the first thing in my mind is that it looks so close, so similar to what I have learned in Quiver representations, so geometric representation theory. And also it looks also very close to geometry. So then the motivation of this project is that, so what is the relation with geometry of Quiver representations? And so I would like to investigate whether our mathematical knowledge in Quiver representations can help to understand more about deep learning and maybe find some more useful algorithms. All right. Okay, so the plan of my talk is the following. So first, I will introduce what are Quiver representations and their moduli spaces, and I will develop the algorithm of deep learning over the moduli spaces. And a very important ingredient is metric over the moduli space. And I introduce some very explicit metrics, and I will talk about uniformization between different metrics. Okay, and then finally, I will talk about some experiments that show in certain situations, running deep learning over moduli space can have some advantage. Okay. And here is a diagram that with how we think about framed Quiver representation. So it's kind of like a machine that acted on by an algebra consisting of the algorithms. And here, these are the framing that acts like the space for input, outputs, and memory. Okay, and you have transmissions between the reality and the machine. Okay. All right, so let's start. So let me start with this familiar picture of a neural network that is very familiar to data scientists. Okay, so we pass inputs into layers of neurons, and then there are transmissions between the layers of neurons, and gradually the machine gives an output. All right, so this is a very familiar scenario. So this pretty much like look like already Quiver representations. So in Quiver representation, what we do is we fix a directed graph. Let's call that Q. So that's called a quiver. Quiver just means a collection of arrows by word. Okay, so we fix a directed graph Q, and a Quiver representation associates vertices with vector spaces and arrows with linear maps. Okay, so these are the vertices, and they are associated with vector spaces, and the arrows are associated with linear maps. So basically, this is also what we do for neural network. Oops. Hello, can you hear me?
I can still hear you. The slides are back.
Okay. Yeah, the screen suddenly blacked out, and then now it's back. I hope you see my shared screen still.
Yeah, I see the screen.
Yes.
Yeah, it's okay.
Good. Sorry for that. Okay, nice. And then, okay. So if you fix the vector spaces associated to vertices, okay, or actually because every vector space is just isomorphic to Cn, let's use complex numbers as our base field in this talk. Then you just fix the dimension vector. Once you fix the dimension, then you fix the vector space, basically, up to isomorphism. Okay. So then you consider the vector space of Quiver representations. Okay, so you just parameterize all the matrices associated to arrows, and that form a vector space. So this home from V tail of the arrow to head of the arrow just means vector spaces parameterizing matrices associated to the arrows. All right. Okay. So we use this notation RQ to denote the vector space of Quiver representations. Any questions so far? Okay, good. And deep learning is running over this vector space of Quiver representations. So you just run stochastic gradient flow over this RQ, the space of matrices associated to arrows. Okay. Another important concept associated to Quiver is the path algebra. Okay, so it consists of paths in the graph. So this is a directed graph, and so there are many possible paths. So for instance, this is a path, right? Okay, so a path can be denoted in this way. Okay, so you read from the right to the left. So it goes from A0 up to AK are the arrows in the path. Okay. Okay, and path algebra is the formal linear combinations of paths over complex number C. Let's say we use C as the base field. Okay. Okay. All right. Okay, and then we fix certain vertices to be our input and output vertices, and we consider also a fixed path that starts and ends with the input and output vertices. Okay. Then, okay, so basically we fix a path. Then by composing the matrices associated to the arrows, we get a canonical linear function, right? So once you fix a Quiver representation, just means a collection of matrices associated to the arrows, then you get this canonical linear map associated to the given elements in the path algebra, all right, by composing all the arrow linear maps along the path. So this is very simple. And then representation learning, or you can also call it deep learning or whatever. So it is to approximate a given continuous function. So K, let's say, is a compact subset inside the input vector space. Okay, and then this is a given function in real life. Most of the time, this is just statistically given. And then what we want is to minimize the distance between the machine function and this given function, f. All right. So we want to minimize this so-called cost function by taking a stochastic gradient descent in the space of representations. Okay, so this is the so-called representation learning. So running this process, then you get a Quiver representation that gives the best linear approximation, because so far we are just talking about, well, composition of matrices. Okay. All right. And then an insight from neural network is that, okay, to get nonlinear approximation, you introduce nonlinear activations at vertices. So some function like this, or the most popular nonlinear function would be ReLU function, like this. But anyway, so you compose with your favorite nonlinear activation functions at vertices, and then compose in certain way, and then you obtain a network function. So this function would be nonlinear then, right, to approximate the real life function. Okay, so this is the process of representation learning. Okay. Let me remark that such a nonlinear structure is actually encoded by a near ring. So namely, so you recall that we consider paths in the Quiver that forms an algebra. So this is the path algebra. So the algebra just means that your product of paths are given by concatenation. Right? So that's the algebra. However, now you are also given with nonlinear functions. So to encode this, you enlarge the path algebra by these nonlinear symbols. And the point is that composition of nonlinear functions are not distributive, right? So if you add, right, if you add two functions and then you compose with a nonlinear function, certainly you cannot distribute them, right? So that's why it forms a near ring rather than a ring. And actually, you can formulate the language over near ring, and many things like forward propagation, backward propagation, and so on can be formulated using near ring. But this is just a side remark because this is not the main point of this talk. Okay. So just from this introduction, you already see that, okay, it looks like related to many areas in mathematics, like representation theory, stochastic analysis, Riemannian geometry, Morse theory, and so on, right? Non-commutative geometry, mathematical physics, and so on. So it looks very much related to math. And as I have said, my motivation question is that I want to investigate, are there any deeper geometric structures in the subject? And can modern geometry provide new insight and enhancement of methods? So most of the talks in the morning have focused on the data, on the input data, which are very interesting. So like applying machine learning to learn mathematical structures. So this is about the input data. But this talk basically focus on the machine itself. Okay, we focus on the deep learning process itself, mathematical structure of the deep learning process. Okay. Okay, maybe the main difference, starting difference between deep learning and Quiver representation theory is that in math and physics, we work with moduli space rather than just the vector space of representations. Right? So recall that this vector space parameterizes all the representations, okay, of the quiver. But in math and physics, it is important to identify isomorphic representations. Right? So then we need to quotient out by the automorphism group. Okay. So instead of just considering the space of representations, we identify isomorphic representations as the same point. So we quotient out by this group G, where G is the automorphism group at each vertex. Right? So on each vertex, there is a vector space, Vi, let's say, and then we consider the group of invertible matrices acting on this vector space Vi. So this is the group GLVI. And then, of course, for each vertex, you have such a group, and you just product them together. So this forms a pretty big group. And then you quotient out by this group. All right. So this group identifies isomorphic representations. Okay. And actually, you need to take stable points more precisely. But in this talk, I don't want to spend time on talking about stability condition. So let me just skip this point. So you need to take away certain points in the space of representations to make the space nice, to make this moduli space nice. Okay. All right. So this is commonly used in math and physics. So we use this moduli space rather than this vector space in math and physics most of the time, because isomorphic representations are supposed to give the same result, so we should identify them as the same, right? Then a very natural question is whether we can run deep learning over the moduli space rather than this vector space, right? So running over the vector space is the common practice, but whether we can change it to the moduli space. So the good thing that why I want to do this is that, well, it better match with math and physics principle. So that's what I have learned in most of my time in math and physics. And also the moduli space is compact in many cases. So actually a moduli space of quivers were started by kings. Okay. And then also later on in this talk, we also will see that actually the moduli space we talk about and this vector space of representations can be uniformized. Okay, basically they are related like the relation between a sphere and a plane. So the moduli space would be more or less like a sphere, and this vector space of representation is like the plane. Okay, so actually they can be uniformized. Okay. Any questions? Okay, so however, we face some immediate obstacles to run deep learning over the moduli space. So first of all, look at this cost function. So this is the distance between the machine function and the given real-life function. So they are this is a function on the vector space of representations. well, it does not descend to the moduli space. Because for the moduli space, recall that we need to identify points which are identified under automorphism group at the input and output vertices, for instance, right? So you have input vertex, you have output vertex, and then you have group of invertible matrices in the input and output vertices. And you wish this function to be invariant in order to descend to the moduli space. But unfortunately, it is not, right? Because for instance, the real life function does not commute with automorphism group in the input, right? There's no reason that if you do some scaling, then the real life function remains the same, right? Or some arbitrary shearing, right? So there's no reason that it remains invariant. And also for this machine function, right? So they are not invariant under input and output automorphisms. Second is more serious. So the activation function are not G equivariant, okay, for the middle vertices. So now we consider middle vertices. Recall that we consider activation functions in middle vertices, okay. In order to be equivariant for this machine function, then you better have activation functions that are equivariant. That meaning that it satisfies this equality. Unfortunately, there's no reason that it satisfies the equality. So in general, it is not equal. So it is easy to understand, right? So sigma is a nonlinear function, and G is some matrix, some linear map. There is no reason that, and actually this almost certainly not true, that a nonlinear function commutes with, let's say, rotation, right? That's impossible, okay, or scaling. That's impossible. This is nonlinear function, right? And so it is not G equivariant. Then there's no hope that this descend to the moduli space, right? It's simply not true. Okay, so in the naive way, we cannot simply descend to the moduli space. And our previous paper with George Jeffreys provided a simple solution to overcome these obstacles. Okay. So the first point is about non-invariance under the input and output automorphism groups. So actually, this is easily solved by using framed quiver representations. So adding framing to the quiver representations. So this notion was first invented by Nakajima and then further studied by many groups of people like Crowley, Bovey, and Reineck, and many other groups of people. Okay, so what is a framed quiver representation? Well, it is what we have said. So a quiver representation, which are just linear maps associated to arrows, but we add with framing. So we consider linear maps going from fixed vector spaces to the representing vector spaces. Okay, so let's recall that for each vertex, we equip it with a vector space, right? And then we have arrow maps, we have linear maps associated to arrows, right? Now we additionally also add a data of framing. Okay, so this is another vector space, call it CNI. Okay, and EI is the linear map that between the framing and the representing vector space VI. Okay, so putting them together, that means the space of framed quiver representation would consist, so a point in the space of framed quiver representation would consist of arrow maps W, together with framing map E, right? Framing map E. Okay, so that's the space of framed quiver representations. Okay, and similarly, we do a GIT quotient, we do a group quotient to obtain the moduli space. Okay, and so this would be the moduli space we mostly work with. Well, what is the advantage? Why does it solve the problem? Well, basically, we think of this EI as providing a basis for VI, for the representing vector space VI. Okay. So actually, do you see my screen dark becomes black out? Maybe it's still stable in the.
I can see the screen.
I see. Okay, so it just happened that sometimes I see black screen. Okay. Okay, so all right. So why is it better, right? So we think of EI as providing basis for the state space VI. So one way to think about it is the following. So look at this picture. One way to think about it is the following. So you think of VI as state spaces of the machine, right? Like in quantum computing, not very fancy. So you think of these as state space of the quantum particles, right? So, and they do not have preferred basis. So the point is that they are basis free, right? So these are the state spaces. And then you also kind of think of the framing, this framing as providing them with basis, or you think of them as vector spaces in reality. So they contains the input, output, or memory. Okay, so these are the framing vector space. All right, and then this is the state space of the machine. Okay, and then this is the algebra or nearing of the algorithms. So algorithm lives inside this nearing or algebra. Okay, and it acts on the state space. Okay, and then EI are the framing map. So that's kind of so communication between the real life framing space with the state space of the machine. Okay, all right. So we kind of think of framed quiver representation in this way in machine learning. Okay, so this would provide a model for the machine. Okay. Now the thing is that now VI are now equipped with bases coming from the framing. Okay. Then these maps, so this is the machine map and this is the real life map, can be descended to this moduli space. Because recall that previously the obstacle is that automorphism group at input and output vertices would destroy, right? So would destroy these functions. They are not invariant under those groups. But actually now, because they are provided with bases, you distinguish vector space with different bases now, right? And so now these functions would be well defined over moduli space of framed quiver representations. Okay, so this is the simple solution for the first obstacle. Okay. So from now on, we consider framed quiver representations. Okay, so representation with framing. Okay. And most of the time, we take the framing dimension to be just the same as the representing dimension, or adding one if you want to accommodate a bias vector. Okay. All right. And the second obstacle, recall that the second obstacle is that the nonlinear function, the activation function, is not equivariant, right? In general, it could not be. So to overcome this, what we do is we will use universal bundle over the moduli space, and also we equip the universal bundles with metrics. Okay. So what are universal bundles? Okay. So first of all, the notion of vector bundle means that we associate each point in the space with a vector space, okay? And we glue them together, glue this vector space together. So these vector spaces vary smoothly as we move around this point smoothly in the space, in the manifold, right? So that's the notion of vector bundle. So just family of vector spaces over the space. Okay, and universal bundle is easy. So recall that each point in the moduli space is parameterizing representation, quiver representation. So each point in the moduli space associate a vertex with a vector space and associate an arrow with a linear map, right? So a point in the moduli space is a representation. And now it's also equipped with framing. Okay. Now, what you do is that you simply take the representing vector space at a given vertex, at a fixed vertex. Okay. And then, so each point, now you have a representing vector space, and then you just patch them together. You just glue them together. That forms a bundle, vector bundle, called universal bundle. Is there any question? So this would be an important concept that we will use later on. Okay, so we simply patch the representing vector spaces together over the moduli space of representations. Okay. Okay, so we have this universal bundle. And then the arrow map would also patch to vector bundle maps between the universal bundles, right? So arrows passes data between the vertices. Now each vertex is associated with a universal bundle. Let's call this I, let's call this J. Right? Then the arrow maps would patch together to give a vector bundle map between the universal bundles. Okay. Good. Okay, so basically we have this picture. Now the framing can also be understood in this way. So recall that framing is just a linear map from a fixed vector space to the representing vector space, right? Now the representing vector space patches into universal bundle. Then the framing map is also a bundle map between the trivial bundle. Now the framing is understood as trivial bundle over the moduli space. And the arrow map would be a bundle map between this trivial bundle to the universal bundle at that given vertex. Okay. So everything can now be understood as universal bundles and bundle maps. Okay. And so basically what we have is this picture. Okay. So we have the moduli space in the bottom, and then it parameterizes representations, and we patch the vector spaces, representing vector spaces together to form universal bundle, and then the algebra or nearing acts on this universal bundle, right? So a path acts on this universal bundle by composing the bundle maps, right, of the arrows. And then the framing would be bundle maps between these trivial bundles. That is parameterized basically the vector spaces in real life, right? To this universal bundle over the vertices. Okay, so we have this picture. Okay, so how does this picture help? So previously, recall that the problem is that the activation function is not invariant under automorphism group, so it does not commute with G, right? So now the thing is that instead of regarding sigma as simply a function, we regard it as a fiber bundle map between these universal bundles. So recall that VI are now universal bundles, and now we can consider fiber bundle map rather than simply map between vector spaces. So what does it mean? So it means that rather than simply considering maps from V to V, we consider maps from this product to V. So the first vector, R framed, is the vector space of framed representations, right? Okay, so that just means that we consider function that not just depends on V inside the vector space, but it also depends on points in the representations, in the space of representations. Okay, so sigma depends both on the input vector and also the representing matrices. Okay, and we require it to satisfy the G equivariance in this way. So basically you think of it as pulling out G to front. So we fix a graph and input and output vertices and representing dimension and framing and the algorithm, that means the path basically, and the fiber bundle maps, which are the activation functions. And then by simply composing the arrow maps and the fiber bundle maps together, then we get a bundle map, fiber bundle map from the input universal bundle to the output universal bundle. Right. So, okay. Now, what we want actually is a map from a fixed vector space to a fixed target vector space, right? Rather than these universal bundles. So what we can do is that we simply compose with the input framing map and the output framing map. Now the thing is that the input framing map is in this direction, so we can simply compose now, right? So we just compose and get this map, that's correct. However, the output framing map is going in this direction. We want to reverse it, right? We want to reverse it so that it goes to the fixed vector space, the framing vector space at the output. Okay, actually this confuses us for a while in the beginning of the project. And well, but actually it's easy. Well, we just take the adjoint, right? We simply take the adjoint map. So the adjoint map appears here, and then we compose. Then we get a fiber bundle map from the input fixed vector space to the output vector space, framing vector space. Okay, is that clear? So in this picture, we can explain in this picture. Okay, so in this picture of universal bundle, what we do is we are given with certain input data. We pass it to the machine using the framing map. Okay, and then we fix an algorithm, and then we act on this universal bundle using this algorithm by composing the arrow maps. And then we take the adjoint, we take the adjoint at the output vertices to go back to the output framing. Then this gives a map from the input framing vector space to the output framing vector space. Is that clear? Right. Okay. Now the point is that to take the adjoint map, we need a vector bundle metric. We need to fix a vector bundle metric to define this adjoint. Okay. Also, another point is, well, I just told you that if I'm given a fiber bundle map, then I can do this. But how to construct an explicit fiber bundle map, playing the role of activation functions, which are very important, right? So how to construct this fiber bundle map? So one way is the following. So what we do is the following. So instead of fixing the function, the nonlinear function, on the representation vector space, we fix it on the framing. So this is the given vertex. We have some representing vector space for that vertex. And then recall that we have framing map, right? From C and I, from this framing vector space to the representing vector space. Okay. So what we do is, so the activation function, instead of putting it on the representing vector space, which is not well defined, it is not invariant under the group action. It is not invariant under automorphism. So instead, we put it on the framing. Okay, we put the activation function on the framing. Then what we do to obtain a fiber bundle map is the following. So we simply take this composition. So, okay. So given a vector inside the representing vector space, you send it back to the framing using the adjoint. And then you act by this nonlinear function on the framing, right? And then you send it back to the representing vector space. Then in this way, you create an explicit fiber bundle map. Okay. All right. Is that clear? So you see that taking this adjoint is very important in both constructing this fiber bundle map and also to compose to get this machine function. Okay. So this would be the machine function. Okay, is that clear? Okay, so with all these ingredients, then this finishes the definition of this network function over the moduli space. All right. And then the second part would be, okay, then we need to So now we have this cost function defined over the moduli space now. Okay, before in traditional approach, it is defined on a vector space of representations, but using this bundle maps and so on, framing and so on, now it is well defined on the moduli space of framed quiver representations. Okay, and the second part would be, okay, and then we need to run a gradient descent, right, for this function on the moduli space. Now this moduli space is no longer a vector space, so we need also a metric, okay, on this moduli space. Okay, and then the gradient vector would be modified under this metric, right? So this is the familiar formula for defining gradient vector when the metric is non-trivial. Okay, you take the inverse of the metric, inverse of the matrix, metric matrix, multiplied with the usual partial derivatives. Okay, so this gives the new gradient vector field written in local expression. Okay, all right, so summarizing, so the two ingredients we need to run deep learning over the moduli space would be, we need a vector bundle metric on the universal bundles, and we also need a Riemannian metric on the moduli space. Okay. Okay. Perhaps let me be very quick on this example because of time. So this would give, so this is an example of AN quiver, a very popular quiver, so what we have talked is that we pass data from the input vector space to this quiver and then compose with the arrow maps and the activation functions at the framing and so on to obtain this network function. Okay, well, to compare with the more popular picture of neural network, actually you can do the so-called Abilization process, which is a well-known process in Quiver, study of Quiver. So what you do is that you simply replace each vertex with a bunch of vertices. This number of vertices is exactly just the same as the representing dimension. Okay, so that now each vertex, after doing this process, each vertex has representing dimension 1. Okay, so this is a process to replace a non-abelian group to abelian group C star, because now the representing dimension becomes just dimension 1. So the automorphism group over each vertex would simply be C star, which is an abelian group. So that's why we call it Abelianization. So by doing this process, then actually the AN quiver recover the familiar picture of neural network. Okay. So let's be quick on this example because of time. Okay, so now let's talk about the main ingredients that we need. So we need a vector bundle metric on the universal bundles and the Riemannian metric on the moduli space. And the good news is that actually we can write down very explicit metrics which have nice expressions purely in terms of the quiver. So this is the theorem that this expression would give a well-defined metric on the universal bundles. Okay, so notice that this expression only depends on the paths in the quiver, so it is pretty canonical. So here gamma, here what we do is we fix a vertex I, right? We have the corresponding universal bundle Vi on that vertex, and then we consider all paths going to this vertex. All paths going to this vertex. So for instance, this is a path going to this vertex. We just compose the arrow maps to get this W gamma. So W gamma is the composition of the arrow maps along the path. Okay. And then we also compose with the framing map E at the tail of the path. Okay, so this is the framing. So T stands for tail. Okay. Okay, and then we do this expression. Okay, so this gives a matrix, and then we just multiply with the conjugate matrix. Okay, so this gives an overall square matrix, and we take the inverse. Okay. All right. So this expression, explicit expression, purely in terms of the quiver, would give a well-defined metric on the universal bundle. And another good news is that actually we just need this. So if you take this, the so-called Ricci curvature of this metric that has an explicit expression, then this would define a well-defined metric on the moduli space. Okay, on the moduli space. So these would give the main ingredients that we need to run deep learning over the moduli space. Okay. All right. Then we have this network function then. Okay. So because of time, I guess I don't want to really talk in detail about the explicit expression. So instead, let me use an example to help you to remember. So in this very simple example of Quiver, which is a quiver consisting of only one single vertex, and together with a framing, and the dimension is very simple. Let's say just C2 to C. Okay, so very lowest possible dimension almost. Okay, then in this example, H is simply this expression, norm x squared plus norm y squared, and then take inverse. So the Ricci curvature of this is simply the standard metric on the sphere. Okay, in this case, the moduli space is simply the sphere. Okay, and the metric we talked about is simply the standard metric on this sphere. So you can regard the expression before is like a generalization of this metric. Okay, and actually H itself is the standard metric on the dual tautological line bundle. But actually, so let me skip this point. Okay. All right. Any question? Okay. Well, so far we have developed an approach using the moduli space. And then now I want to relate back to the original Euclidean setup. Okay. So actually, the original Euclidean setup can be understood as a chart of this moduli space. So this moduli space is a manifold. And a manifold is patched by charts. Actually, the space of Quiver representations, this vector space, can be understood as a chart inside this moduli space. And so the original learning is performed in this chart using trivial metric, using Euclidean metric. Okay. So in application, the representing dimension is set to be bigger than or equal to the representing dimension. Okay, so then the framing can be written in this way. So the framing is a rectangular matrix. You split it into a square matrix, and the rest, actually in application, the rest part would be the bias vector. Okay, and then we can use automorphism to make the square matrix to be simply identity matrix. Okay, so actually in application, the framing would take this form. Okay, so this is the bias vector, and this is simply an identity matrix. Okay. All right. Okay, so what I want to say is, okay, so the Euclidean learning is actually part of the game. All right, so uniformization gives a unified point of view towards the original Euclidean space, the moduli space that I have introduced, and actually another one which plays the role of hyperbolic disk. Well, generalization of that. Okay. So basically, the point of view can be understood by this very simple example. So we have three things. One is the sphere, one is the Euclidean space, okay, and one is the hyperbolic disk. They can be uniformized. So recall that the sphere, well, mathematically it is space of lines in C2, okay, so this is called the complex projective line, okay, so space of lines inside C2. So this is, okay, so this is the vector space C2. Okay, so you just consider arbitrary lines in C2 and you collect them together, so this forms CP1. Okay, now if we equip C2 with a non-standard metric, with an indefinite metric, so y squared minus x squared, okay, instead of plus, Then you can consider space-like lines. So those lines in the directions where this metric is positive definite. Okay. Then actually the lines have to be inside this light cone, so-called. Okay. So then if you just consider this set of lines that are positive definite, then this forms the hyperbolic disk. Okay. And similarly, if you consider this indefinite metric, you simply omit the term x squared. Then, okay, then you get the Euclidean plane. Okay, so if you consider lines that are positive definite under this indefinite metric y squared, then it has to be in this direction. It cannot be horizontal, and each such line would correspond to a point in the plane in the line of level 1. Okay, so it hits the line of level 1 at one point. So each such line would correspond to a point in the horizontal line. And so this gives the Euclidean plane, okay, C. This gives the Euclidean line C. Now we are using the base field C. Okay. I try to draw something, but okay, anyway, yeah, let me give up to draw. Okay, all right. Okay, so this is classically well known for symmetric spaces. And actually, this embedding from the disk to the sphere is well known as Borel embedding, very classical, well studied. Okay, and then we can generalize it to framed quiver moduli. So basically, we just take an indefinite metric in this flavor. Because of time, let me just, well, be very brief. So such kind of expression would define an indefinite metric, and you consider positive definite representations under such metric, then that would define three kinds of moduli space. Okay, so the point is that what we talked about is the positive definite kind, is the usual, right, spherical kind, and then actually the Euclidean and hyperbolic one appears if you use these expressions of metrics, indefinite metrics, okay, on the space of representations. Okay, any questions so far? And then they can be connected in a family, right? So you simply make a parameter m here. So basically, it is like the sphere. So this parameter m is like, well, the curvature, right? So if the radius of the sphere get bigger and bigger, then it's gradually goes to Euclidean space, and then if m gets negative, then it goes to hyperbolic space. So this is generalization of this kind of picture. Now, of course, this is very high dimensions, but basically it is generalization of this kind of picture in mind. Okay, good. And so we can run deep learning over these spaces, right? So now what we do is doing some experiment that we regard m as a learnable parameter. So this parameter is the parameter for the metric, right? So we try to learn them in the process, okay? So these are remarks that well, non-Euclidean geometry has been very important in learning graphs and word embeddings, and also homogeneous spaces was also used by this group of people, Cohen, Geiger, Weiler, to make use of symmetry of input data. But here, what we are focusing is not the input data. We are focusing on the space of representations itself. Okay, we are focusing on the machine itself. So we are talking about the moduli space and the non-compact dual. Okay. All right. So let me go to experiments very quickly. So what we do is, okay, we implement it by codes. Actually, we simply add just around 10 lines of codes to the original one. Very simple. Okay, so these m's are the metric parameters that we want to learn. So these are learnable parameters. And then we have the metric h, bundle metric h, right? And recall that we just multiply the usual output y at a vertex by this bundle metric h, basically. Okay. Okay. Okay, so this is the forward processing. And then also, so this is first part that we modify, so the bundle metric. The second part is the Riemannian metric on the manifold, on the moduli space. So what we do is simply that we need to change the gradient by this formula. So change the gradient by this explicit formula. Okay, so this would be the gradient under non-trivial metric on the moduli space. And we test it on CFAR 10, and then in these models, maybe because of time, I can just say that, okay, in these models, implementing this bundle metric and metric on the base, then there is some advantage over the original approach. Note that the number of parameters are around the same, right? So actually for convolution layer, we do not so the number of parameters just remain the same. And for dense layer, there is more parameters that corresponds to bias vector. So just a few parameters, and then we gain this advantage in validation accuracy. And then actually we do more experiments. Let me go very fast. And get better testing accuracy. But for big model with big data, we expect that the advantage would gradually disappear because after all, it is just a few parameters. So what we test, we go into the direction of small data that when suppose that not enough data is given, so whether this perform better. So it turns out that this new method gains a better result in several models, in VGG models and so on. Okay, but yeah, that's time's up. Let me end here. Actually, I also want to talk about some interpretation, but because of time, let me just stop here. Okay, thank you.